Today we're going to continue looking at properties of functions, which again is a review. And we are going to introduce a new property. Well, it's not really a new property. We looked at even and odd symmetry in Algebra 2, but in Algebra 2 we looked at it graphically. Today we are going to look at even and odd symmetry algebraically. So what I'd like you to do is to please turn to page 11 in your packet, pause the video, sketch the graph, and find the properties. Okay, so at this point, you should have this done, and we're now going over it. You should know that the graph of 1/2 raised to the x power is a exponential decay function. It's got a point at 0, 1. Again, if you just made yourself a table, you'd be like, boop, 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 1, 1, and then that's 1/2. And then 1/2 squared is 1/4. And you'd be like, oh yeah, this is exponential decay. And the other side, if you had a really accurate graph, remember 1/2 to the -1 power is like 2/1 to the first power. Oh, that was an 11 or a 21. Which is just 2. So that's what your graph looks like. And this will be a 4. And goes up, so on. I once had a student tell me that, like, they kind of think about it like they when they have to do the negative powers, they just continue the pattern backwards. So they know that the pattern is multiplying by 1/2 or dividing by 2. So when they go backwards, they multiply by 2. So like 1 times 2 is 2, and then 4, and then 8, and then so on. Okay, so this is what our graph looks like. It has a domain of all real numbers because every x value here has a y value. It does not have a range of all real numbers. It has a range of 0 to infinity where neither value is included. So you also could write that just y is greater than 0, whatever you prefer. We have a horizontal asymptote here at y equals 0. Because it's physically impossible to raise 1/2 to a power and get nothing. So we have an asymptote there. Because of that asymptote, we say that this function is bounded below, and its end behavior, let's see. Well, on the right, as x goes to infinity, well, over here, as x goes to infinity, y is approaching that horizontal asymptote at 0. But on the left, as x goes to -infinity, y is going up, it's approaching infinity. So again, I'll do a little highlight for you. Here, the right, as x approaches infinity, that we're looking here, and we see y is approaching 0 because of this arrow. And when I'm looking at the left, as x approaches -infinity, I'm looking here. And when I'm looking for my y value, I see that it's up here. So that's the end behavior. So as again, as a review, we did this in Algebra 2. End behavior describes what is happening to the function as it approaches positive and negative infinity. And the other property, as I said before, that we're going to look at today is even and odd symmetry. Now I want to point out there are lots of different types of symmetry. You can have symmetry around a variety of lines or rotational symmetry around a variety of points. Even and odd symmetry is very specific. Even symmetry means that the graph has symmetry around the y-axis. It is mirrored over the y-axis. So for example, this parabola has y-axis symmetry. This point matches up with boop, that guy. Now I could have a parabola that looks like this. I'm just going to draw a random parabola. It's symmetrical around this line that goes through the vertex. Sorry about that. Let's keep going. So again, this parabola over here, it has a line of symmetry. There's that dotted line of symmetry, but it's not around the y-axis. So I would not call this an even function. All right, this is not even. So we're just going to erase it and make it go bye-bye. Were you bigger eraser? It's going to take a long time. Aha. All right. So if I'm looking for an odd function means it has 180-degree rotational symmetry around the origin. So this also said with respect to the origin. So for example, actually not for example, I'm going to say 180-degree rotational symmetry. Okay, so when I look at these two functions that are left, this one in the middle, it has rotational symmetry. Like I can clearly see that this piece, if I rotate it a certain way, would probably match up here, but it's not around the origin. Won't, won't. So we say that this function is neither even nor odd. Now this guy here, here's the origin, and this happens to go through the origin, it doesn't have to go through the origin. If I kind of take this point right here and I rotate it 180 degrees, it lands down there. If I were to pick up this point and rotate it 180 degrees, it lands down here. This function has odd symmetry. The graph 1 divided by x, which looks like this, it doesn't go through the origin, but it has odd symmetry. You can see how this, let me get the highlighter actually, how if I took this curve and I rotate it 180 degrees around the origin, it matches up perfectly. So that's another good example of an odd function. Okay. So what I'd like everyone to do is I want you to pause the video and I want you to fill in as many properties as you can for number 1. At this point, you should have paused the video and tried to fill in as many properties as possible for number 1. When I look at the domain, it's not going to be all real numbers because I see I have a vertical asymptote here at x equals 0. So here we go. The domain is going to be all real numbers. Oh, that is a light color. All real numbers, x cannot equal 0. Now, when I look at the range, I see just like the warm-up, I see I have that horizontal asymptote. I think I said x equals 0. That was a mistake. It was y equals 0. And everything above it, I have a y value for. So I have 0 to infinity, or you can write y is greater than 0. So that asymptote, again, is at y equals 0. And this one is bounded below. Does this graph have even or odd symmetry, or does it have neither? You should have answered that it has even symmetry. I'm going to pick some points, like this point right here matches up with this point right over here. I have this point here, it matches up with this point here. And you can see, like, if I were to fold this graph along the y-axis, it's going to match up perfectly. Now, unlike the warm-up, both sides of the graph head towards the horizontal asymptote. On the right, as x goes to infinity, y goes to 0, and on the left, as x goes to negative infinity, y also goes to 0. Number 2, we are provided with the graph of the natural log. As a reminder, ln stands for natural log. Go ahead, pause the video and fill in as many properties as you can. Hopefully for the domain, you realize there is literally nothing on the left side. So it starts at 0 and it goes to infinity. You could also write that as x is greater than 0. But now the range, the y values go from the bottom to the top. So the range is all real numbers. Because the range is all real numbers, it goes from bottom to top, this function is not bounded. It does have a vertical asymptote at x equals 0, like right here. Right there. There's my vertical asymptote. Symmetry, this graph does not have even or odd symmetry. It is not reflected over the y-axis. It does not have 180-degree rotational symmetry around the origin. So you can say none, or you can say neither. And behavior on the right, as x goes to infinity, y is going up. On the left, I like this one, as x goes to negative infinity. There's nothing here. Look at that, there it is. It's a big old vast emptiness. So we are just gonna say y goes to, you can say NA, not applicable. There is no left side of this graph past the vertical asymptote, so I'm not worried about the left end behavior. I'm going to turn the page to read the directions, but then I'm going to go back to this graph. We are now going to algebraically determine if a function has even or odd symmetry. To do this algebraically, we are going to plug in negative x and simplify. Then we're going to look at what we get, and we're going to compare it to the original equation. If plugging in negative x gives the same function, make a little note, gives original. If it gives the original function, your function is even. If plugging in f of negative x gives the complete opposite, the function is odd. Here's why. If I look at this even function, if I have the point 1, I have this point is 1, 1. Now, if I plug in negative 1, what's the y value? It's buddy. It's also 1. So if I plug in the positive version of 1 or the negative version of 1, I get the same value. That's what we mean by saying it gives the original. Okay. Now, if I have an odd function, and I'm just going to draw one down here. Actually, I'm going to go over here. I'm just going to make one up. Looks pretty good. Let's say that this is the point 1, negative 2. If I put negative 1 in here, I should get positive 2. And sure enough, I've graphed this. I've made it so that it's the point 1, negative 1, positive 2. That's what I mean when I say it gives the opposite. Now, if you don't get either of those two patterns, your function is not even or odd. So let's take a look. My first function is x squared minus 5. So I'm going to plug in negative x. So I'm going to write f of negative x, and you have to write it the way I'm writing it, is negative, and I'm going to make this, instead of just saying negative x squared, sometimes I like to put a 1 here for a coefficient because it helps me out. Like negative x and negative 1x are the same thing. So when I square this, if I square negative 1, I get 1. If I square the x, I get x squared, and then I bring down the 5. And I see that this function is exactly the same as x squared minus 5. That means this function is even. So now for letter B, we're going to plug in negative x for g of x. So 5, I'm going to do the same thing. I'm going to put a net, like not just negative x, negative 1x. I don't know. It just kind of helps me when I have to cube. And then negative, I'm going to go negative 1x. Every time I see an x, I'm going to put negative 1x there. So go ahead and cube negative 1x. Hopefully, you got negative 1 cubed is negative 1 and x cubed. Now here, when I did, there's no like power up here, so I'm just going to distribute the negative and I get plus 1x. Now 5 times negative 1x cubed becomes negative 5x cubed plus 1x. So let's take a look. The original function was positive 5, negative 1. This function is the opposite, negative, positive. That means this function is odd. All right, go ahead and try to plug in negative x for letter C and unpause the video when you're done. Okay, hopefully you did letter C on your own and you're like, wait a second, this is weird. Negative 1 squared is 1. X squared is x squared. 4 times negative 1x is negative 4x. So Mrs. Strauss, what do I do if one term is the same, like I got x squared, but one term is opposite, well, that means that this function is neither even nor odd. So we've had one of each. Let's see how J turns out. So -2, -1x cubed plus 4. So go ahead, pause the video, go all the way to the end, make a decision, even, odd, or neither. Okay, at this point, you should have tried it on your own. And we have -1 cubed is, oh, I should not have done this, I should have done. Is -1, and then x cubed, 4 times -1 is -4. -2 times -1 is +2 x cubed minus 4x. Oh, look. Negative, positive, positive, negative. This one is also odd. Let's write 2 more at the bottom. Let's write f of x equals 3x squared minus 8. And let's write letter F. F of x equals x cubed plus 2x. Oh, wait, that's a mistake. So why don't you pause the video and try both of these? Okay, so again, I want you to try these on your own. And then hopefully you see, all right, well, if I square -1, I get +1. So this is 3 times 1x squared minus 8. So f of -x is 3x. Hey, this is what I started with. This is even. Again, pause the video. Try letter F on your own. So if I go -x, -1x cubed. So let's see, -1 cubed is -1. -1, oh wait, oops, typo. What the heck, Strauss? That's a big eraser. Must be squared and outside. -1 squared is +1, and then x. So let's see, this one, this one's neither. Your homework tonight is to complete page 14. Please make sure you complete the whole page. There's a bottom also. And go ahead and make sure you check your answers and your work on Google Drive.